we present HanDyVQA, a video benchmark for fine-grained hand-object interaction dynamics. HRI recognition has many important applications, including activity recognition and monitoring, skill assessment and training, XR, and robotics. To support these applications, AI systems need to accurately understand detailed hand-object interaction dynamics. Existing HRI recognition benchmarks can roughly be divided into two categories, low-level and high-level. Low-level understanding focuses on the geometrical understanding of hand and objects. High-level understanding focuses on the semantic understanding of HOI. However, the high-level understanding mainly focuses on relatively coarse-level recognition, and they often miss the dynamic process that connects hand manipulation and its effects. This motivates our benchmark, HanDyVQA, HanDyVQA. The key idea is to evaluate fine-grained HOI dynamics reasoning spanning from manipulation to effect aspect. HanDyVQA introduces 6 complementary question categories. The first 3 questions focus on manipulation, action, process, objects. The remaining 3 focus on effects, location, state change, object parts. In addition, we introduced 2 tasks. The first one is multiple choice question answering. The second is reasoning video object segmentation, or reasoning VOS. The reasoning VOS requires the model to segment objects or object parts based on the reasoning about the interaction dynamics. The slide shows an example of action category. This question requires understanding process motion and interaction targets. This slide shows an example of process category. This question requires understanding hand and object motion. And this slide shows an example of object parts category. This question requires understanding the structure of objects and spatial relationship. Here's how we constructed the benchmark. We built HanDyVQA on top of the Eagle4D dataset. First, we used narration annotations to detect videos containing hand-object interactions. Second, we generate question candidates using GPT-4 Mini. Third, human annotators carefully verify the generated questions and provide the correct answers. For object and object parts questions, they also annotate segmentation masks. Fourth, GPT-4 Mini generates distractor options. Finally, human check and revise all questions and options. This collaborative pipeline allows us to efficiently generate large-scale annotations while maintaining the high quality. Here's the dataset statistics. Compared with previous datasets, HanDyVQA uniquely covers both manipulation dynamics and effect dynamics. In total, our benchmark contains more than 11,000 QA pairs, and all of them are fully checked by human. Another important point is diversity. We cover diverse scenarios and interaction types. Using HanDyVQA, we evaluated current video models in MCQ and reasoning VOS tasks. Here we compare 2 major types of video language models. The first one is dual encoder models, and the second type is video models integrated with large language models. The quantitative results showed that all models perform far below human performance. Even Gemini 2.5 Pro, the best performing model, achieves only about 72.6% average accuracy. In contrast, humans achieve more than 96%. This suggests that the current models still struggle to capture subtle hand-object interaction dynamics. To better understand model limitations, we analyze failure cases. We identify 4 major error types. The first is confusing nearby objects or hand size. The second is failure to capture spatial relationships between hands and objects. The example shows that the model fails to understand that scraper is interacting with thin wood instead of the wall. The third is missing motion dynamics. For example, model fails to recognize object movement directions. The example shows that model confuses the hand movement in directions. The fourth is failure to recognize structural or state changes. The example shows that model failed to capture the state change of the tent zipper. We also analyze the effects of frame count and resolution. Overall, using more input frames and higher resolution improves performance. However, some models quickly saturate. For example, Unplug03 shows limited improvement beyond 8 frames. This is likely because its visual encoder was trained with only 8 frames inputs. We also analyze error trends. Interaction and spatial relationships errors remain the most difficult. Increasing frame count resolution generally reduce the errors. However, open source models still struggle to effectively utilize additional temporal information for motion understanding. Now I'll move to the reasoning VOS task. In this task, the model must segment objects or object parts based on the question. We mainly evaluate SA2VA models as LLM integrated video object segmentation models. The table shows the quantitative results for reasoning VOS. Overall, the performance is much lower than existing reasoning VOS benchmarks. Especially, object parts category is extremely challenging. This is because the task requires component-level reasoning, understanding object structures, and recognizing subtle interaction regions. These findings suggest that reasoning about fine-grained HOI dynamics remains difficult even for recent segmentation-capable MLLMs. The model often segments incorrect object regions, over-segment nearby objects, or miss the manipulated object parts. These examples highlight the difficulty of grounding interaction reasoning into precise pixel-level localization. Finally, we investigate whether explicitly adding HOI-related information can improve performance. In addition to RGB video features, we incorporate hand pose information, bounding boxes of manipulated objects, and clip features extracted from manipulated objects. We integrate these HOI cues into the visual representation and fine-tune the model using a small amount of our training splits. We train the model via contrastive learning by using positive answer text and distractors. Overall, adding hand and object cues consistently improves performance across most categories. For example, hand motion improves action and process understanding. Object features help object and state understanding, and combining multiple cues generally gives better average accuracy than using only one cue. However, another important observation is that simply concatenating all features is not optimal. Even when additional HOI cues are available, effectively modeling the relationship between hands, objects, and motion and state changes remain challenging. In conclusion, we introduced HanDyVQA, a new benchmark for fine-grained hand-object interaction dynamics. Our benchmark evaluates both manipulation dynamics and effect dynamics. We also introduced reasoning VOS for object and part level reasoning. Our experiments show that even the strongest current video language models still struggle with spatial relationships, motion understanding, and structural change reasoning. As a future work, training VLMs that are sensitive to precise location, motion, and interaction of hands and objects is important. We hope HanDyVQA will encourage future research on HOI-aware video understanding models. Thank you for listening.